Everyone. Today I'll be presenting a topic on digital avionics, focusing on how technologies like synthetic vision, enhanced vision, and advanced cockpit displays improve situation awareness for pilots. SVS is an advanced avionics display technology that provides pilots with a clear 3D computer-generated view of the external environment. It offers visual terrain awareness, obstacles, and runway guidance even when real visibility is low, such as during fog, night, or clouds. SVS typically uses NASA's Shuttle Radar, Topography Mission, SRTM, data for terrain mapping. When combined with head-up displays, HUDs, SVS provides pilots with an artificial horizon and terrain overlay, enhancing precision during approach and landing phases. The types of data sources are terrain databases, obstacle databases, navigation inputs. Integration with enhanced vision system is when SVS, virtual terrain, is fused with EVS, real sensor imagery. The result is a combined vision system offering both real-time visibility and predictive terrain awareness. SVS is primarily an advisory system. While not typically approved for minimums credit, it enhances situational awareness and may be part of HUD guidance in certified systems. Manufacturers include Garmin Collins Aerospace, Honeywell, Universal Avionics, and M.E Aviation, Falcon Eye system with SVS integration. For example, during night approaches and mountainous terrain, SVS provides a clear 3D synthetic view of the landscape, runway layout, and flight path, even if the pilot sees only darkness out the window. The advantages of SVS are provides clear terrain awareness in all weather conditions. Reduces controlled flight into terrain accidents, enhances pilot confidence during takeoff and landing. Reduces workload and improves operational safety. The applications are: it is used in commercial and business aviation, military operations in low visibility environments, flight simulators for advanced pilot training. Next topic is enhanced vision system EVs. It improves the pilot's ability to see external surroundings using real-time imaging sensors. It penetrates darkness, fog, and rain by displaying infrared or radar-based images of the environment ahead. EVS is often integrated with SVS to create a combined vision system, CVS, which merges real sensor imagery with synthetic terrain visuals. This combination enhances accuracy and realism, offering pilots both virtual and real-world awareness simultaneously. Types of EVS sensors are infrared sensors, low-light cameras. Integration with synthetic vision system form a combined vision system. FAA and EASA approve EVS for enhanced visibility, allowing lower landing decision heights. Manufacturers are Collins Aerospace, Honeywell, Elbit Systems, and Gulfstream. For example, during foggy landings, EVS displays runway lights and terrain details invisible to the naked eye. Components of EVs are infrared camera, millimeter wave radar, image processing computer, enhances the captured images for display clarity. Display, HUD/PFD, pilot interface. Infrared or radar sensors capture live images from outside the aircraft. These are processed by an onboard computer to improve visibility and are displayed on the HUD or PFD. This enables pilots to identify terrain, obstacles, and runways even in zero visibility conditions. These are the advantages and applications of enhanced vision system. Both SVS and EVS improve visibility and pilot awareness, but in different ways. SVS provides a computer-generated synthetic image using stored terrain data, while EVS provides real sensor imagery from the outside environment. When combined, they form a powerful system called combined vision system, offering both predictive and real-time awareness for maximum safety. Thus are the difference between synthetic vision system and enhanced vision system based on their definition, data source, environment dependency, purpose, display, and certifications. Next is the situation awareness. It is of 3 levels. Level 1 is perception, detecting and recognizing elements in the environment, identifying nearby aircraft, weather, or terrain on radar. Level 2 is comprehension, understanding what those elements mean in context, recognizing that nearby aircraft may cause a potential conflict. Level 3 is projection, predicting future status or outcomes, foreseeing that the aircraft ahead will cross the flight path soon. The advantages of situation awareness is to prevent loss of control and spatial disorientation, improves decision-making under stress, Enhances coordination between crew members. Reduces human error in complex flight situations. The applications are it is a integrated cockpit displays. Military and UAV mission systems. Air traffic control and simulation training. The Cooper Color Code is a system that describes different levels of mental awareness and readiness to respond to potential threats. It helps people stay alert and prepared by categorizing their state of awareness into 4 colors. White, yellow, orange. Red-white represents excellent handling and high awareness, a calm but alert state. Yellow shows moderate awareness, manageable workload. Orange indicates reduced awareness and high workload, the pilot needs to refocus. Red means unsafe or overloaded, loss of control or awareness. Originally developed for personal defense, this color system is now used in aviation to help monitor pilot workload and readiness. The next topic is panoramic big picture display. It is created by combining multiple overlapping images taken from different angles or positions into one large, continuous, and wide image. It is commonly used in 3D mapping, photogrammetry, and visual tracking systems to capture a wider field of view than a single camera can provide. It integrates flight, navigation, and system data into one large screen view. It allows pilots to monitor all flight information simultaneously, reducing workload and enhancing situational awareness. Modern panoramic displays use OLED or micro-LED technology for high brightness and reliability. Future designs include curved panoramic displays and augmented reality overlays that combine synthetic vision and enhanced vision data for superior cockpit awareness. The components are integrated display processor, which combines input data from all avionics systems. Wide area display that has large, high-resolution screen showing all flight parameters together. Graphics processor to generate dynamic visuals for real-time updates. Pilot interface, which enables touch or voice interaction for control and customization. When processing the 3D point cloud, 3 key terrain models are generated. DSM, digital surface model, includes natural and built features, trees, buildings, etc., shows surface height. DTM, digital terrain model, represents only the bare ground surface, removing buildings and vegetation. DEM, digital elevation model, a general term that can refer to either DSM or DTM, a digital representation of elevation data. These models are critical for geospatial analysis, urban planning, and environmental modeling. While 3D mapping uses multiple images to build 3D models, panoramic stitching sometimes causes distortion or misalignment, especially if images are taken from different altitudes or angles, if there is camera movement or inconsistent lighting, or the scene contains moving objects. These issues can cause geometry errors in 3D models, though visual tracking movement or features in the image, is less affected by these distortions. The block diagram is the working principle of panoramic big picture display. Visual tracking involves following objects or features across frames using computer vision algorithms. In panoramic or stitched images, since the full field of view is available, tracking performance improves. The system can monitor objects across a wider scene without losing them. Hence, tracking is not a problem, even if panoramic stitching creates minor geometric errors. The software tools used are Agisoft Metashape, Pix 4D Mapper, Drone Deploy, Autodesk Recap, Microsoft IC or Adobe Photoshop OpenCV, Programming Library. The advantages are: provides a unified operational overview, improves crew coordination and safety, reduces clutter from multiple smaller displays, supports reconfigurable layouts based on flight phase. Applications include Airbus A350, Boeing 787, and Gulfstream G500-600 military fighter cockpits, flight simulators, and training environments. Disadvantages are: moving objects cause blur or duplication in the final image, causes image distortion at edges due to camera angle or lens. Curvature, depth and scale inaccuracies affect 3D mapping and DSM/DTM quality, requires high processing power and memory for stitching, not suitable for real-time mapping due to processing delay. Overall, digital avionics and advanced displays provide a unified operational overview, improve pilot coordination, and enhance safety. They are used in modern aircraft such as the Airbus A350, Boeing 787, and Gulfstream G600, as well as fighter jets like the F-35 Lightning II. These systems also play a vital role in simulators and training environments, shaping the next generation of smart and safe aviation technology. Thank you.